Do you want? Thank you very much. And thank you to everybody who is in the room, in the Zoom room at the moment, for attending the webinar this morning. I'm Paolo Bonato. I'm the editor-in-chief of the IEEE Engineering Medicine Open Journal, Engineering Medicine and Biology. And the webinar today is devoted to a special issue that was guest edited by Professor Björn Eskofier. I don't need to provide the detailed introduction of Professor Eskofier because he's very well known in the field, at least among those of you who have an interest for digital health technology. But you might not be familiar with recent work that I believe, Björn, you started a couple of years back in the area of what I call radar light technology or remote monitoring. And that was the topic of the special issue that he guest edited with his colleagues. So I'm very excited about the webinar that we're going to host today. I'm going to ask Professor Eskofier to take the lead. I'll be in the back seat and look forward to all the presentations. So thank you very much, Professor Eskofier, and thank you very much to everybody who's attending today.
Thank you very much, Paolo, and hello to everybody who's listening in. It's fantastic that there's so much interest in our topic for our journal special issue, special paper collection on the topic of how we call it invisible sensing. And that is about radar-based biomonitoring, so touch-free, non-invasive remote sensing opportunities provided by this upcoming and emerging technology. I would like to make a brief introduction of the topic today, and then I will pass the word to our panelists, everybody who contributed a paper to the special issue is here tonight, or for me tonight, for everybody else today. And we'll give a brief presentation, about 5 to 7 minutes, about our special collection papers. And then in the end, we will have a bit of a discussion, a joint discussion about the topic. So please, if you have any questions during the talks, we will not interrupt them. Then please share them in the chat. And in the end, we will have a joint discussion on interesting topics, interesting questions that are coming up, but also, of course, individual aspects of the presented papers as well. So as Paolo nicely said, my name is Björn Eskofier. I co-guest edited this special paper collection for OJEMB EMB together with Martin Fossiek. You see his image on the top right. He's a radar hardware and signal processing expert. And myself, I call myself an expert in machine learning and data analytics for healthcare. I'm speaking to you from Erlangen University, Friedrich Alexander University, Erlangen, Nuremberg, where we are doing some relevant digital health and AI in medicine efforts in order to bring healthcare to a new level. The special issue, as a quick overview, was targeted or was conceived because there is a certain megatrends in the global healthcare systems, or pushing the global healthcare systems to a limit, and those are just summarized in our aging populations in many countries that produce rising healthcare costs, which necessitates a shift to preventive and personalized care, for which we need better data, better monitoring techniques, also more dense data from individuals. At the same time, we have just experienced a global health crisis with the corona pandemic, the COVID pandemic, and what is sure is that the next pandemic is certainly just around the corner. So there is a necessity for research in ambient, non-invasive, and remote sensing technology. There is existing solutions that have been researched wide and far in, for example, RGB camera-based or depth camera-based monitoring techniques, and also wearable sensors, of course. But there is also recently a rising interest in radar-based biomonitoring. And this gave rise to our special OJEMB paper collection, which summarizes some of those emerging technologies and discusses some ethical considerations. Now on the right, you see a nice image how ChatGPT, aka DALL-E, imagines the topic, but I rest assure you that there is more interesting figures coming up in the individual papers. Just to give you a bit of background why we do this, why I conceived this special collection together with Martin Fossiak. We have a research center that is dedicated on this specific question in our region of Erlangen-Nuremberg. So this is the map of the German Republic. And here in Erlangen and Nuremberg, we have a digital health hub as put forward by the Federal Ministry for Economic Affairs. And in this digital health hub, we have a research center, the so-called MKINs, Empathokinesthetic Sensing Research Center, that is targeting motion parameters, as you can measure them, both with existing sensor technology, like, for example, with wearable sensors, but also with camera-based sensing, RGB camera-based sensing technologies, and biosignal monitoring technologies. But then we are also looking at how radar can be an important piece of the puzzle when you want to observe motion parameters, like, for example, macroscopic motion parameters, people that are moving, but also microscopic motion parameters when you, for example, see the jugular vein because of the heart activity, or you see even sweat glands emitting sweat when somebody is stressed. So with these measurements that comprise an outer state of the human, we would like to understand something about the inner state of the human, the behavioral parameters that lead to this outer state via some internal biomedical body layers. Like, for example, you're stressed, you're starting to emit sweat, and you're also starting to change your body posture. So these are effects that we would like to delve deeper into, as I said, with a combination of different technologies, and that gave rise to our MKINs Research Center. So this is happening at Erlangen-Nuremberg University with its partner universities, and we invite you to stop by in our MKINs lab if you're ever in the area. It's about 100 people that are involved in this research at Erlangen University, but also at some satellite universities that we have in Germany. One of them is in Hamburg, and Nils here today with us will also present from Hamburg University. So the research center exists for 4 years now. It will hopefully exist for another 8 years. So a lot of time for you to visit us and to hopefully see a lot of our interesting research. If you don't come around into our area, then of course you will hopefully see a lot of papers coming about the topics from our research center. Now about today, the agenda for today, we already had the first item covered. I gave you a little bit of an overview of the special collection, why it might be interesting and what gave rise to it. Next, Johanna will present the first paper in a short 5 to 7 minute presentation, as well as the other author representatives from our individual papers that were collected in this special collection. And you see here the titles of the papers. So we will have Shangi, Ftinios, Sefi, and Nils that are presenting in this order their individual papers. And then we will have this joint discussion. So please, if you just joined, you can ask questions in the chat, and me and the other panelists will take them after our presentations, and we will have this joint discussion. With that, I'll stop it here, stop sharing, and would like to invite Johanna to the stage, who will give the first overview presentation of one of the research papers that we have. Johanna.
Yes, thank you, Björn. So let's get this going. Welcome everybody also from my side. The paper that I am presenting today basically provides a review and a tutorial on machine learning enabled radar-based biomedical monitoring. And as you have already gotten an introduction from Björn now, this research is part of the collaborative research center MKIN. And just a small recap, with MKIN, we want to capture and model body functions covering both physiological and pathological disease states. Well, and a key focus of this research is to measure human motion parameters at both the macro and the micro levels in a way that is remote and also minimally intrusive. To allow this, we are researching novel sensor technologies as the state-of-the-art in biomedical monitoring methods suffers from several limitations. So current methods often rely on invasive or contact-based techniques, which can be uncomfortable or disruptive. For example, if you look at blood probing to measure stress levels, for example, this might actually induce stress itself, and this might skew your results, right? Further, if you look at marker-based sensors to capture motion, this sensor setup might actually alter the natural movement itself. And also, if you look at cable-based sensors, they are just uncomfortable and impractical. So in this context, remote and contactless sensor technologies will enable continuous and also comfortable health monitoring. And hopefully this will provide a richer and more accurate database. Radar systems address these limitations by capturing motion without direct contact. Radar captures spatial information by transmitting and receiving an electromagnetic wave and measuring its round-trip distance through phase evaluations. This allows the measurement of velocity or Doppler information, as well as range information and also angle information. In the biomedical monitoring context, so far most works have focused on the evaluation of Doppler and range information over time. And this three-dimensional database is often addressed as the radar data cube. Now, if we look at this exemplary walking motion that you have just seen in the video, the radar data that we captured actually shows the range of the person walking towards the radar and then away from the radar over time. Further, we can also see the Doppler distribution or velocity distribution over time, which shows the velocity information of the individual body parts. So we can see a moving body towards the radar as a mean value of this distribution. However, we can also see the swinging arms and legs around this distribution. And we call this representation also spectrogram. And it is a very prominent example in activity recognition. Also, one representation is range Doppler maps, which basically represents both databases that we just looked at. However, what is not visible here is the phase of the received radar signal is also very sensitive. And this means that we cannot only use radar to capture the macro motions, for example, while walking, but we can also detect very small motions, for example, chest displacement due to respiration or also small vibrations caused by the beating heart. And some approaches also use multiple antennas. This is, for example, frequently used in pose estimation. And for this, we get a radar data cube for every antenna. And this allows us to also evaluate angular information. But you may have already noticed that looking at all these data cubes, or even only looking at one data cube, the radar data is not only large in size, it also contains a significant amount of sparsity. And moreover, so independent of the dimensionality of the radar data, interpreting this complex radar data can also be very challenging. And this is where machine learning methods become essential. These models are designed to sift through large complex data sets, and they can help us to extract meaningful features from it. And well, depending on the radar data dimensions and also the desired output that you want to get, the techniques used can vary widely, from simpler machine learning techniques like random forests to more complex deep learning architectures such as CNNs, for example. Well, and combining radar-based macro and micromotion assessment with machine learning-driven analysis then forms the foundation for a wide range of biomedical applications, which we explain in detail in our paper. These applications include localization, pose estimation, that can also be used for gait analysis, as well as activity recognition. In the biomedical context, there's a focus on fall detection. And further, if we can use radar to assess vital signs, this also allows us to identify sleep stages or to classify stress levels. Finally, in our paper, we also emphasized critical ethical considerations that must be addressed when using this technology, if you want to use this technology in biomedical applications. Radar-based technology offers a privacy-preserving advantage over video and camera-based monitoring. Due to its contactless design, it also increases comfort and the achievable accuracy. However, as radar is unobtrusive and often also invisible, the operation also raises essential questions about transparency and maybe the need for informed consent. So if we address these considerations properly, then this research also holds significant potential to advance the field of biomedical monitoring. Thank you very much for your attention.
Thank you very much, Johanna. That was a very informative kickoff presentation for our panel. And now I would like to ask Shangi to the stage. We're looking forward to your presentation.
Okay, great. Thank you so much, Björn, for the introduction, and thank you, Johanna, for kicking off the technical discussion. So with that, I'll start sharing my screen. Can you see my screen? All right, perfect. So I'll do a little bit of introduction regarding the co-authors of this paper. Basically, the contact author of this paper is actually Dr. Changjian Gu. He is currently located in Shanghai, and it's after midnight. That is why I'm here to help him to present this. So he's actually the best person overseeing the vital sign part of the research going on in this joint group. And a little bit background about this lead researcher. So Changjian actually obtained his PhD degree from Texas Tech University about 12 years ago, and his PhD dissertation was focused on vital signs detection. And he had been doing this, continuing this since then. He was a person who integrated Ftinios radar sensor chip into Google Pixel 4 phone to enable that for remote monitoring of hand gesture commands. And after a few years at Google, he joined academia and is leading a strong team at Shanghai Jiao Tong University, also collaborating in hospitals, carrying out further research with a focus on clinical applications. So here is a brief roadmap envisioned by this research group. And basically, as we have seen, radar can be applied to different scenarios for different type of healthcare applications, covering a very broad spectrum of users, from newborns all the way to the elderly. But I think what is really interesting on this page is the vision laid out by the authors. Basically, the authors think potentially the first short or medium term of real practical application on human subjects would be focused on hospital and nursing facilities, on medical grade application. And the reason for that is we do need supervision and the sort of familiarity or expertise in using the device, because presently vital signs detection biomedical radar still face challenging of complexity in the setup, especially noise and interference caused by ambient environment and also human body motion. And because of that, we think it would be more appropriate to deploy biomedical radar in clinical applications, starting from medical grade with supervision from nurses and healthcare providers. But eventually, the long-term goal is we're going to make, with the help of AI, machine learning, advanced semiconductor technology, we are hoping that in the long term, this technology can really enter our homes for widely deployed home consumer grade type of application. Okay, and with that, I will talk a little bit about technical foundation or for the studies carried out here, and we call this Doppler cardiogram. And I think one of the first uses of Doppler cardiogram was published in 2019. And the basic idea is the chest wall displacement due to ventricular and arterial volume change is going to induce this Doppler effect. And basically, the radar can remotely pick up motion related to core information coming from the heart, the ventricle, and also the atrium movement. Okay, and one important and valuable thing about this is that the signal we detect is mechanical activity of the heart, as compared with the more common usage contact-based ECG, which is electrical activity. So from our point of view, our vision is that Doppler radar actually offers a complementary data source, specifically focusing on mechanical movement. So we are not really trying to compete or replace ECG. Instead, we are hoping this mechanical activity detected by Doppler radar can give health providers another degree of data to further strengthen and enhancing future healthcare. Okay, and that being said, let's look at several biomedical applications. The first one is the detection of systole time intervals. Basically, from the Doppler cardiogram, we can pick up those key points. In ECG, it was well known that there are points P, Q, R, S, T, and from there, medical health providers can extract very important information. From the Doppler radar point of view, people started looking at Doppler cardiogram, and later on they found out it would be really beneficial to analyze the differential signal inside DCG, basically the dynamics of the signal, because by analyzing differential DCG, you can suppress the noise and interference coming from respiration of the patient. Okay, and as I mentioned earlier, for common type of application, Doppler radar still suffers, if we talk about vital signs detection, still suffers from noise and interference coming from human body motion. So the first step we have carried out for clinical application was focusing on patients after surgery, after operation. So shown here is an example. This patient actually had heart problem. So after surgery, after operation, she was recovering from the process and she was put into deep sleep. And during the process, we applied biomedical radar to monitor the vital signs, specifically focusing on cardiac signal, and demonstrated very good agreement with contact-based ECG signal. Okay. And here are the data, pretty impressive data, but the catch here is the patient was not moving. And the research group further moved on. So in this review paper, we also talked about premature heartbeat PHB patients sort of diagnosis, as well as diagnosis for atrial fibrillation patients. Okay, so shown here are actually two different case studies. On the left side is for PHB patients, And as we can see in this graph, this is the error plot between ECG and the Doppler cardiogram. And as you can see, most of the time they agree very well, except for very strong spikes shown here at 2 moments. And as a matter of fact, those 2 moments do not tell us if ECG was failing or Doppler was failing. As a matter of fact, that was the moment we capture premature heartbeat. When there is a premature heartbeat, both methods struggle to find out a clear peak. And this is actually the moment that is helpful for doctors to tell if the patient is having this type of symptom. Okay, and on the right-hand side is a detection of artificial fibrillation. And shown over there, basically, this is a regular, this is a good patient without any problem. And on the right-hand side is the Lorenz plot for a patient who does suffer from AF. Okay, so as a matter of fact, those are textbook type of detection, but they were obtained by biomedical radar. So this is quite encouraging for the biomedical radar community. Moving on to the next page, we focus on preterm infant detection, again in hospital environment. So this baby actually suffers from very strong intermittent hypoxia problem. Basically, this was oriented from apnea. So in this study, biomedical radar was able to precisely capture those events. And I'll skip the complex block diagram and the results. You can get more information from the paper as well as the paper referred in the review paper. But what is quite interesting to the community is that the study demonstrated apnea can be detected much earlier than the drop of blood oxygen. This is quite important, but to me, I think this is actually a no-brainer because advantage of biomedical radar is that it captures mechanical motion of the chest, of the heart, of the entire body. And this actually captures the source of blood oxygen drop, right? So basically, biomedical radar is more advanced. It will react faster when apnea happens to warn health providers to take action, okay? And along this line, the research group actually carried out more study, again, in clinical environments that focused on sleep apnea detection. And we all know that sleep apnea has different types. And in this paper included in the review, we actually compared 3 different scenarios: COPD, central sleep apnea, as well as obstructive sleep apnea. And we used biomedical radar to monitor the patients, along with conventional expensive contact-based PSG. So as you can see, biomedical radar was able to clearly identify different types of apnea. Like the bottom side are radar measured result. As you can see, different patterns can be recognized from real-time monitoring results. And it also agreed very well with PSG data. Okay, and along that line, we looked at sleep staging. Not only research academia group are doing this. As a matter of fact, Google kept putting biomedical radar sensor into their devices and started 2 years ago. You can buy Google Hub 2, and inside Google Hub 2, there is a radar sensor chip that does the same thing. It monitors patients overnight, and it can tell different stage of sleep. So hopefully in the near future, a lot of people do not have to wear a smartwatch. Instead, placing a device along the bedside is going to be sufficient to tell different sleep stage and provide health data, basically data to healthcare providers. Okay, and finally, this is sort of a big leap. From cardiac activity monitoring, we can further push for biomedical radar to remotely capture blood pressure as well. But again, the catch here is we have to start from very specific case for patients after surgery, after operation, when they were not moving at all, then we can extract very high quality data. And by looking at pulse wave velocity, looking at the waveform, other parameters, there are actually different ways of extracting blood pressure. So in this paper, it was demonstrated you can actually get a very good reading of SBP as well as DBP, very reliable data in those specific clinical cases. Okay, so with that, I believe I have finished my review of this review paper. Thank you so much.
Thank you very much, Shangi, for the review of the review. Next on stage is Ftinios, who is going to present passive radar sensing for human activity recognition. They did a survey on this really important topic as well. Ftinios, are you ready to rumble?
Yes, thank you. Let me share my screen first.
We can see it, thank you.
Thank you. So hello everyone, I'm Ftinios and I'm going to present our paper, Passive Radar Sensing for Human Activity Recognition and Survey. In this paper, we provide an overview of the passive radar system architecture, the signal processing techniques, feature extraction and machine learning methods that have been used for human activity recognition. We discuss key challenges associated with passive radar sensing and explore possible future research directions. So let's begin with the motivation for using passive radar for in-home healthcare. So as the global population of elderly people increases, it makes a demand for modern healthcare models that use innovative technologies to monitor the health status of people in their homes. So these approaches preserve the autonomy and independence of elderly people and chronically ill people, and improve their overall well-being. Assistive living technologies also promote proactive care, allowing for the early detection of signs related to worsening health conditions. However, the existing sensing technologies such as wearables, video camera, sound-based sensors have several limitations. For example, wearable devices need to be carried by the user, which causes inconvenience issues or compliance issues. And video cameras record plain images of the subject and the surrounding environment, which raises privacy concerns. Additionally, vision and sound-based sensors may be affected by environmental conditions such as the background noise or the lighting. Passive radar and radar system in general address most of these limitations and are a strong alternative for assistive living solutions. Radar is a contactless tool, meaning that the user doesn't have to interact with any electronic devices. Radar data are more difficult to interpret than image data, which improves the perceived privacy from the user. Also, a radar system can use existing signals such as the Wi-Fi passive radar approaches, which minimizes infrastructure costs. Both active radars and passive radar systems have been studied for activity recognition, but this system has several differences. An active radar uses dedicated transmitters and high bandwidth signals, which are optimized for radar detection. This approach means that an active radar requires a frequency band within the radio frequency spectrum, which may cause interference with the existing systems. On the other hand, the passive radar uses third-party signals that already exist in the surrounding environment. But this approach means that passive radar has limited control over the transmitting signal, which signal is usually optimized for effective data transmission rather than radar detection. Let's try to understand how a passive radar works by looking at the typical architecture of a passive radar system. A typical passive radar consists of two channels. The reference channels capture the signal transmitted from the third-party transmitter, and it is connected to a high-directional antenna that is steered toward the third-party transmitter to avoid multipath and effectively recover the transmitting signal. On the other hand, the surveillance channel captures the signal reflected from the user and the surrounding area. These signals are processed in order to extract range Doppler information for activity recognition and detect moving targets and separate the desired movement from the unwanted stationary reflections from the surrounding environment. In passive radar system, to extract range and Doppler information, we use the cross ambiguity function processing, which is implemented by performing the fast Fourier transform on cross-correlated reference signal and the signal reflected from the target. The range resolution is typically limited because it is limited by the bandwidth of the wireless signals that are used as third-party transmitters. In this figure, you can see an example of a spectrogram from a passive Wi-Fi radar. And in activity recognition applications, typically we use Doppler spectrograms or extract fixtures from a Doppler spectrogram. The signal processing flow for a passive radar system consists of one more key step, which is the direct signal cancellation. This is necessary because the strong signal transmitted from the third-party transmitter often masks the weaker reflections from the target. And so most radar systems use an algorithm called clean algorithm, which is an iterative approach that subtracts a phase-corrected model of the reference signal from the original data in order to suppress the direct signal interference. So the next step in the flow of activity recognition is feature extraction, which is an essential step because it helps extract meaningful information from the complex Doppler data. And this is essential because it directly affects the robustness and accuracy of the classification models. The majority of the studies directly use the Doppler spectrograms in the classification models. And while this approach preserves a lot of details, it requires more complex models, and typically deep learning models are used. Another approach is to extract meaningful information from the Doppler spectrogram, such as the duration of an activity or the maximum Doppler shift. And these features provide information that can be easily interpreted, but they often lack diversity, which makes challenging to differentiate between similar activities. Other techniques that have been studied in the literature is dimensionality reduction techniques like PCA or SVD, and machine learning and deep learning methods for automatic feature extraction, which are very promising tools, but they require a high computational power and larger training datasets, which make difficult the deployment in real-time and resource-constrained applications. Regarding activity recognition, the majority of the studies use data obtained from isolated activities and not continuous measurements, which are more realistic. And also the lack of an open data set and the diversity of the data set and the processing steps that each study has performed makes difficult the comparison of the results between the studies. So traditional machine learning methods such as supervised methods like SVM and unsupervised methods like K-means have been used in many papers, and they have been applied in simpler feature sets. For the deep learning, the most common approach is to use CNN models along with Doppler spectrograms as an input. But other deep learning models such as LSTM and transformer architecture have been applied and show promising results. Another valuable tool is transfer learning, which involves using a pre-trained model and adapting it in order to a specific activity recognition task. This is valuable because it improves accuracy and also reduces training time and the amount of the training data that are required. Recently, some studies have started exploring sensor fusion techniques by combining information from different sensors like radar, vision, or RF sensors. And this approach improves the accuracy of the activity recognition because it mixes the dataset with information from diverse sensors. So to conclude, passive radar sensing is a promising tool for home healthcare. However, there are several challenges that remain. As I mentioned, the majority of the studies use isolated activities, and the activities are recorded in control environments. So future model should transition to recognizing activities from a continuous data stream and be tested in more realistic and diverse environments. Also, multi-user environments have unique challenges because in these settings, the radar signal consists of overlapping motion patterns, which should be separated in order to detect motion from different people. In the context of active radar system, techniques like blind source decomposition, blind source separation, and direction of arrival detection have been studied, but for passive radar systems, they have not been studied, such techniques. Privacy is also a serious challenge for passive radar sensing because its non-intrusive nature implies that the individuals may not be aware that they are being monitored. And future studies can also explore its own communication and sensing framework in which wireless signals can use for both efficient data transmission and radar detection operations, right, like activity recognitions. And finally, there is a need for an open and comprehensive dataset for benchmarking the different algorithms and enabling the comparison, the comparison of the result across all the studies. Thank you very much.
Thank you very much, Ftinios, for this comprehensive overview of activity-based monitoring techniques. And with that, I would like to give the word to Sefi. Sefi, who's going to present on an overview of radar-based gait parameter estimation techniques for fall risk assessment. Sefi, we see your slide view. We see your presenter view. Perfect. No, we see the correct slide view, I mean. You're still muted.
Can you hear me now? Can everyone hear me now?
We can hear you.
Okay, awesome. Yeah, thank you very much. My name is Sefi. I'm currently an associate professor at the University of Alabama. A lot of the work that you will see in this presentation was conducted at the University of Alabama, but since then, all of us seem to have kind of gone into different places, as you can kind of tell from the affiliations on the slide here. Right now, Dr. Martelli, my collaborator, is actually doing research at MedStar Health in Maryland, and the entire lab is actually about to move to North Carolina State University in January, where we will be kind of growing up in scale as we become part of a larger center that has to do with wearable sensing and rehabilitation. So exciting times to come. This paper specifically gives an overview of radar-based techniques for gait parameter estimation. The specific parameters we've extracted in this work are extracted with the consideration of fall risk. However, this does have broader and more general applications, as we can consider that gait parameters affect a wide variety of different types of health monitoring applications. So if we think about the significance of gait for health, we can see that it has a number of important applications, not just to kind of the detection of critical events, such as falls, which has really become, like, I think, a focus of a lot of radar research over the past decade. But it also has the potential to grow into some new and emerging areas, such as early warning of neuromuscular disorders, trying to predict whether or not older adults have fall risks, and also for evaluating disease progression and post-treatment monitoring. So you can imagine if someone has a stroke and we want to assess the efficacy of treatments post-stroke, we can continue monitoring the gait to see if the gait has returned to a more normal kind of state, and other types of operations, whether it be a hip replacement, knee operation, or any other kind of intervention, can be evaluated through the assessment of gaits. And so gait is an important metric for our health. And if we consider how currently we try to evaluate this, you have physical therapists, which will do kind of visual or stopwatch-based observations with things like the time up and go test. Or if you might have in like a university setting where there's a research laboratory, maybe you have some kind of clinical quantitative gait analysis methods using treadmills, force plates, more expensive motion capture systems, which is often used in the research context for motion analysis. But when you consider from the point of view of the patient, you know, these types of facilities are typically very far away. They're not easy to access, especially in, you know, rural Alabama. Hospitals like this might be 2-3 hours away. Getting care in these types of facilities would be costly and infrequent. So when we consider all of these challenges and the fact that in order to really develop some of these more kind of pioneering techniques with radar towards especially the early warning and rehabilitation, we really need to find a way of being able to get gait parameter estimates on a continuous fashion, on a more frequent fashion, in a method that is low cost and more widely applicable. So this really drives our aim for trying to work on techniques for in-home gait analysis. So again, this will enable, you know, the lower cost of healthcare, greater accessibility, as well as a source of continuous stream of gait data that can really, I think, open the groundwork for much more advanced radar applications. The figure that we have below here for the in-home QGA kind of shows what we envision long-term, where you have something that is, again, invisible. The radar might be mounted on a wall or on a desk, and maybe works in conjunction with wearables and other technologies that are available in the home. As some of our earlier speakers have so eloquently shared, however, there's obviously a lot of challenges in trying to do in-home gait analysis, which is very coupled with the problem of in-home activity recognition as well. It was just mentioned how it's important that we're able to assess activities from a continuous stream of data, because human motion is sequential and you get a constant stream of it. So we have a lot of work that's been done in the area of activity recognition, continuous monitoring, sequential recognition, and especially trying to address problems of AI/ML and the training of robust person-specific models in this context. The specific paper that we've contributed to this special issue, however, is focused on gait parameter estimation in particular, and especially trying to assess the quality and the accuracy of the gait parameters that we access from radar data. There's been a number of works, especially over the last 5 years, that propose different techniques for gait parameter estimation. But an important gap in the literature is that a lot of these works are not really comparing or evaluating errors with respect to gold standards. There's a lot of papers who use markerless systems such as the Kinect cameras for the purposes of reporting errors. And while that type of assessment may be adequate if you're considering, smart environment applications or IoT applications where you just need to have like a general idea of what a person is doing in the room, when we're considering medical applications, we really do need to consider more specifically what the estimation accuracy is, and we need to compare this against gold standards. So this paper that we've submitted here does the kind of initial pilot study where we collect a small number of participants, but we are acquiring data with a radar system, and we're comparing against a Vicon system for gold standard comparisons. So the specific study here that we've done an assessment on considers 6 participants in particular. Again, we're using a Vicon system that has 8 cameras. And the radar system that we're using is the TI's Cascade radar, which is a somewhat unique radar system in that it's commercially available. It's originally designed for automotive applications. So as such, it can give you a very high degree of resolution in the azimuth direction because you're able to use time division multiplexing MIMO techniques to generate a virtual array of 192 channels. This, therefore, in a spatial sense, has great advantages, but as we'll see through our assessment presented in the full paper, it has the disadvantage that it doesn't give you a very high rate of gait parameter estimates. In other words, it has it's very slow in terms of its temporal resolution. And when we're considering gait parameter estimation, this trade-off of spatial resolution versus temporal resolution becomes an important consideration. These types of things are discussed further in the paper itself. One kind of innovation that we have in this paper, which kind of really helped us, was that we proposed a technique for using simulations to be able to actually train the deep neural networks that are used for estimating the skeletal key points. The initial paper where we proposed this method was actually done earlier in 2019, and we extend it for the purposes of gait parameter estimation in this paper. So I kind of refer you to the details of both papers for understanding how the simulations are done. But the key point in this is that we do the data augmentation process on the skeleton itself. So we apply scaling in the time axis, scaling in the physical dimensions to account for different body type sizes. And we also do a Fourier-based parameterized approximation to each of the joint trajectories in velocity and apply perturbations to these parameterized trajectories to be able to generate a large number of physically consistent simulated samples. Note that these samples are derived from mocap measurements themselves, which were obtained from Vicon data. But if we only have, let's say, 5, 10 participants, in this case, 6 participants, with maybe only a handful of samples in terms of actual measurements, this diversification techniques allows us to generate tens of thousands of simulated samples, which we're using to train the models for skeletal estimation. We look in particular at parameters such as stride time, step length, and their variability, and we compare the errors using 2 different types of methods for extracting these parameters. In the first method, we derive it from the RF skeletons that we estimate. And in the second method, we derive it from the microdoppler signatures, because the microdoppler signatures are a much more widespread way of doing gait parameter analysis in the literature. So I'll kind of defer you to the paper for the details of what those quantitative comparisons are. But we do have a nice discussion at the end of the paper where we just share our insights in terms of what the current limitations are. And we discuss hardware-based limitations, deep neural network-based limitations, as well as the environment-based limitations that are due to some of the in-home considerations, such as the presence of obstacles, the fact that we need to do segmentation of sequential data. And in terms of hardware limitations, we discuss how our use of this high-resolution radar kind of affected our estimation accuracy and what some of the trade-offs, again, between temporal resolution and the spatial resolution are. And as part of future work, we suggest looking into expanding this study into the consideration of radar networks. This is something that we're planning to do in an extension of this work in the early spring of next year, where we're going to be conducting another study with participants in the MedStar Hospital, where we have multiple radar sensors with different transmit waveform parameters to offer more insights into the hardware-based limitations of the gait parameter estimation. We're also doing, in our future work, additional work on actually the deep neural network design itself, trying to take a look at how we can integrate biomechanics and other physics-based parameters to improve the accuracy of our deep neural networks in their ability to be able to get gait parameter estimates. So again, I encourage you to look at the details of the paper for more discussion of this, as well as our future work coming out next year, which continues this line of research. Finally, I'd just like to acknowledge the National Science Foundation, which has supported all of our work, and I welcome all of the participants to take a look at our website and to feel free to email me if they have any further questions or would like to discuss anything in this domain. Thank you very much.
Thank you so much, Sefi. And that is indeed a very good paper to read, as the rest of the papers in the special collection are. I can attest to that. Last but not least, we will have Nils Albrecht on stage. And since we are running a bit short of time, we will not have a very long discussion at the end. I will just do a quick wrap up. But we hopefully have time enough to listen to Nils's presentation. And if not, this webinar is, as you've seen, recorded and will be available on the OJEMB website. And with that, I will give the word and the stage to Nils. The stage is yours.
All right. Björn, thank you so much for the introduction. I'm Nils Albrecht. I'm with the Institute of High Frequency Technology at the Hamburg University of Technology. And this paper was created also within the CRC MKINs. And it's called EMRAD, Ubiquitous Vital Sign Sensing Using Compact Continuous Wave Radars. It's a little bit of a different publication than the others, so there's not a review paper, but a little bit more technical. So I will just give a very soft technical introduction, then talk about the research gap we are filling with this publication, and then present some results and applications we are targeting with it. So using vital signs radar for vital sign sensing, we've heard this already a couple of times today. And in general, the principle is pretty simple. So you use the most basic radar you can do is a continuous wave radar. So you have an oscillator, you transmit a signal from some kind of antenna, you beam it at the person you are measuring, get the reflections, and then compare the phase or the amplitude from the signal, do some digitization, and afterwards you have your digitized data. And what you're actually measuring is the distance from the surface you're measuring, in this kind, the chest of the human body, in comparison to your antenna. And there's a very simple formula to relate the phase you're measuring to the distance. And in theory, of course, that means you can just estimate this distance very precisely and just look at the modulation of the distance. And for vital signs, there's three main aspects. One is the breathing, which is very obvious. If you breathe, your lungs expand and therefore your upper body. And the other two big important signs are created by your cardiovascular action. So when your heart is beating, your blood pressure is changing, which expands or collapses your blood vessels, which is a tiny movement in the realm of hundreds of micrometers. And then there's one more thing, which is the heart sounds, which are, as the name suggests, are sounds, but sound is just vibration. And therefore, if you just look close enough, you can actually see the vibration on the surface. And this is usually in the micrometer or even nanometer regime, so it's pretty small. So even if you have a very sensitive radar, you need to look very closely to see those heart sounds. But the heart sounds are the most precise thing you can get because they have the best timing accuracy. The problem is we have a little bit of a scale problem because, as Shangi mentioned it, there is a lot of research going on, but most of it is dealing with people at still, so no large body movements. And there is very obvious reason, because large body movements are in the orders of meters of magnitude at worst case, but heart sounds are in the order of nanometers to micrometers. So we are certainly at a scale problem. And there is a need for data, because this vital sign sensing is commonly researched a lot, but the key technology to enable real measurements is, of course, machine learning, because there is currently no conventional signal processing technique to enable to extract those tiny movements from the heart action from like large body movement and separate it. So basically everything is turning into machine learning. And as we know, machine learning is a data-driven approach, so you need a lot of data to do so. And of course, you need to gather this data in real-world applications. So you cannot expect to collect data just in a very specialized lab environment and then apply it to real-world scenarios. So you need to get this data to improve on training. So what we present in this publication is a system which focuses on the scalability as well as the performance and measurement. So enabling a lot of different applications. So what we do is we have radar nodes, which are the front ends with containing the individual radars. Then we have a synchronization node, which takes data from a lot of sensors, combines it, and has also the possibility to combine it with other sensors, because a lot of applications where you need to get gold standard reference data, for example, an ECG or whatever you name it, you need to synchronize it very precisely, because if you want to extract individual heartbeats, you're in trouble if you're not able to synchronize your reference data with the radar data very precisely. And this is a huge issue in a lot of applications. And then, of course, if you want to gather a lot of data, you need to have the back end to gather all the data, collect it, organize it, and also the usability, for example, in a clinical setup where there's multiple persons using it, and scaling it up is not so easy. Just a very brief overview about the technical aspects of the radars. So what we are doing is we are combining a commercial transceiver, which has antenna on package, so it's very compact, very cheap and lightweight. And then we're combining it with very advanced integrated packaging technologies. So we're having the integrated transceiver on the board, then we're transferring it to a rectangular waveguide, and then to an SAW waveguide, and having an external antenna on top, all in a very compact footprint, which enables us to build like a lot of these sensors pretty easily, with very good measurement performance, and having an antenna which is dedicated to the purpose of measuring the vital signs, which is very important. On the right, you can see the sensor itself is pretty small and can be made to a bigger scale. Now I'll present some of the applications we are using the sensor setup within our project MKINs. So for example, we have a part of it is monitoring sleep. So in this case, 6 of those sensors are mounted underneath the bed and on the side of the bed. And there is, of course, a gold standard reference, so measuring the sleep stages at night and comparing the data from the radars. We have setups where we have stress studies and use the radars in front, for example, in front of a chair, to measure the heart rate and the heart rate variability of the person. But we also do more basic research and having the radar mounted on a gantry, being able to move it around and measuring at different positions of the body. And due to the very precise synchronization, we can look at the propagation times of the pulse waves and heart sounds around the body. And all of this is kind of equipped with a neural network, which we trained on the data which we already gathered within the project, which is an LSTM-based classifier, which kind of predicts every individual heartbeat. So you can see pretty much the raw data on the top with just from pre-filtering. And what the network outputs is a score of predictions if there is a heartbeat or not. And then when you compare it to the ECG signal, you can clearly see they overlap very, very well in this setup. And if you compare the interbeat intervals from these data sets, you can also see that you can estimate a instantaneous heart rate very precisely. So not only an average heart rate over a couple of seconds or minutes, but you can do it on a beat-to-beat basis. So if you're interested in that, I would suggest have a look at the publication. There's much more detail in there, and if you have any questions, feel free, of course, to ask them. So I think this concludes the presentations. And I think
correct.
I will hand it
Thank
over
you
back to
much.
Björn.
Yeah, thank you very much, Nils, for this also very concise and comprehensive overview of your publication. And with that, I will just conclude the webinar with a short wrap-up. We discussed a bit already behind the scenes and in the chat, but please do reach out to individual authors. They are all really responsive and, of course, happy to answer further questions about the individual papers. We saw some really interesting technology and also algorithms that are, of course, summarized in those papers that are available in the fantastic IEEE Open Journal of Engineering and Medicine and Biology. Our special collection is called Invisible Sensing, Radar-Based Biomonitoring. So there you will find all those fantastic papers that were just presented. We discussed a little bit the necessity to share data sets. We also saw that quite a lot in our research at the MKIN's Research Center, and many other authors are echoing that. So if you can, please do share your valuable research data with the world. That will make accelerated research possible and help us push this technology, this really interesting technology of radar-based biomedical monitoring into existence in clinical use even faster. But please also do consider the ethical dimension in your research, as we have patient groups in our monitoring that needs to just be taken into account. With that, I would like to thank all the individual presenters. These were fantastic presentations, Johanna, Shangi, Ftinios, Sefi, and Nils. I would like to extend to you a very warm and very loud digital applause. That was fantastic. And of course, always when people present about their research, it gets a little bit too long. So please excuse that, but I think it was very, very exciting and worth the time. I would also like to thank the webinar team, Virginia, Federico, everybody else who was behind the scenes. You did a fantastic job in organizing us, which is not that easy. And of course, also making a great webinar happen for the community. And in general, I would like to thank the team at the IEEE Open Journal of Engineering in Medicine and Biology, and in particular, Dr. Paolo Bonato, who made this all happen. This is really a great chance, and we hope that we filled this particular opportunity to your expectations. And now that's it from us. I do wish you a great day wherever you are on this planet. Thank you.